An adult takes about 12 breaths per minute, inhaling roughly 500 milliliters of air with each breath. The molar compositions of the inspired and expired gases are as follows. Inspired gas, oxygen 20.6, carbon dioxide 0, nitrogen 77.4, water 2%. Expired gas composition, oxygen 15.1, carbon dioxide 3.7, nitrogen 75, water 6.2. The inspired gas is at 24 degrees of the centigrade and 1 atmosphere, and the expired gas is at the body temperature and pressure 37 degrees of the centigrade and 1 atmosphere. Nitrogen is not transported into or out of the body in the lung, so that the nitrogen in is equal nitrogen out. Calculate the masses of oxygen, carbon dioxide and water transferred from the pulmonary gases to the blood or vice versa per minute. Calculate the volume of air exhaled per milliliter inhaled. At what rate is the individual losing weight by merely breathing? We start our process from drawing a process flow diagram. We have the stream entering the system, air inhaled, and we have stream out, which is exhaled air. The composition of inhaled stream or inhaled air is shown here, and the process conditions for the inlet stream are 24 degrees of the centigrade, which is equal to 297 kelvins and 1 atmosphere pressure. Volumetric flow rate of the stream in is equal 6000 milliliters per minute. We know that we have 12 breaths per minute times 500 milliliters per each breath. That give us the value of 6000 milliliters or 6 liters per minute of the air inhaled. The process stream output conditions are 37 degrees of the centigrade and 1 atmosphere. Composition of the exhaled air is given here, and it was given in the table on the previous slide. Since we know volumetric flow rate of the stream going into the process, we don't know molar flow rates in and molar flow rates out. Why do we need to look at the molar flow rates? Is because the composition of the exhaled and composition of the inhaled air is based on the molar fractions. So in order to go from the volumetric flow rate into the molar flow rate for the incoming stream, we have to use the ideal gas equation. We know the temperature, the pressure, the volume, so we can take either the approach that the PV is equal nRT, and N, which is the molar flow rate, would be equal to P times V divided by R times T, or we can go and use the STP, standard temperature and pressure conditions, and use formula from the ideal gas equation that allows us to calculate the molar flow rate of the stream entering the process as the function of system pressure, temperature and volume, as well as the STP conditions for the pressure, specific molar volume and the temperature at the STP conditions. So when we substitute the numbers into this equation, we would end up with the molar flow rate of the incoming stream that is equal to 0.246 moles per minute. Now we have to calculate the masses of oxygen, carbon dioxide and water transferred during this process. So when we look at the nitrogen balance, we know that the nitrogen is not participating in the process of the exchange, so nitrogen in is equal nitrogen out, and running the component mass balance on the nitrogen, nitrogen in is equal nitrogen out, would give us one equation with one unknown, 0.774 times 0.246, where 0.246 is the molar flow rate of the stream in, is equal 0.75, which is the percentage of the nitrogen leaving the process, times unknown molar flow rate. So running the nitrogen component mass balancing the process, which is equal to 0.254 moles of air exhaled per minute. Now we have to look at the component mass balances for the oxygen, carbon dioxide and water. For oxygen balance, we will have to look at the oxygen in minus oxygen out and the molar basis times molar mass of the oxygen, and this would be equal to 0.394 grams of the oxygen per minute. Carbon dioxide balance is our carbon dioxide out, since our carbon dioxide in is 0, so the carbon dioxide molar flow rate is 0.254 times 0.037 moles per minute times molar mass of the carbon dioxide, and this would be equal to 0.414 grams of CO2 per minute. Water balance is water out minus water in, because the molar flow rate of water out is greater than the molar flow rate of water in. Therefore, we have to set up our balance as the output minus input. Output minus input times molar mass would give us 0.195 grams of water per minute coming out of the process. The next question here is calculate the volume of air exhaled per milliliter of air inhaled. So we would set up the ideal gas equation for the inlet and outlet into the process. So our PV in is equal molar flow rate in times R times temperature in. And when we take the ratio of PV in over PV out, that is equal to N in RT in divided by N out RT out, pressure would cancel off, the gas constant would cancel off because the pressure is 1 atmosphere. So our equation would be volumetric flow rate in over volumetric flow rate out would be equal to the molar flow rate in times temperature in divided by the molar flow rate out times temperature out. So substituting the numbers, we have calculated the molar flow rate out and in, and we know the temperatures of the process. Our final number would be 1.078, which means that we will have 1.078 milliliters of air exhaled per 1 milliliter of air inhaled. The last question is, at what rate is the individual losing the weight by merely breathing? So we have to set up a process flow diagram that allows us to see where we are gaining the mass, where we are losing the mass. So oxygen at the inlet, we gain the mass here, and we are losing carbon dioxide and water. So water lost plus carbon dioxide lost minus oxygen gain would give us the required balance. When we substitute the numbers into this equation, the final weight loss per minute would be equal to 0.215 grams per minute.